Hello and welcome everybody. My name is Rudi Grobler and I'm really excited to be here with you today. It's incredible, I can't even describe how good it feels just to physically see people actually, but it is really, really nice to be here with you today. Today we are, and the emphasis is on try here, but we're going to try and teach a car to drive itself from point A to point B using a novel technique or novel techniques like deep learning and simple simulation environments like games. Now this is a relatively big topic. Sorry, I just want to start my timer. This is a big topic. It's quite a complex topic. And we're probably not going to get to everything, but hopefully the techniques that we're going to look at can translate to some other fields. Maybe to get us all on the same page, what I thought I'll do is I'll just take my title and divide it into its three main sections. Go into each one of these sections a little bit more in depth so that we have the same understanding, and then hopefully get to demos, and if everything goes well, hopefully drive over stuff. This is quite a complex demo, and it's got a lot of moving parts to it, so it can definitely break, so please just bear with me a little bit here. The first topic that we need to look at a little bit more is the self-driving bit here. And here, self-driving isn't necessarily the focus. It was merely the playing ground on which I tried out AI or deep learning. But it's still a relatively important bit. Self-driving is quite an interesting field, and it's got a lot of research going into it. It's got a lot of movement at the moment. So it's quite an interesting field to start with, first of all. And maybe just as a definition, what I mean, at least for this talk, what I mean by self-driving is simply being able to ask a car to take you from point A to point B. Now, this might mean that you're behind the steering wheel and you have to pay attention for short periods of time, or maybe even, hopefully, sit in the back seat, read a book or text or whatever you want to do. But the general idea is that you ask the car to take you from point A to point B. Now, this isn't an easy problem. It's a way harder problem than I initially thought it would be. And I don't necessarily believe we are completely there yet, but there's a lot of companies doing interesting work here. Self-driving, just to give you a sort of a quick overview, self-driving is defined by levels. These levels, you will hear them often when people talk about self-driving. They're at L2 or L4, it just means what level they are. These levels are from 0 to 5. 0 is no automation, 5 is fully automated. The only difference between 5 and 4 really is if the driver can sit in the front seat or he sits in the back seat. But in general, these are the levels. We are probably not even going to get to 0, to be honest, but we're at least going to try, and that's hopefully the takeaway here. To look at first of all, the self-driving, a lot of people are using different approaches. So you can have, there's many different approaches. And maybe to compare the approaches, what I thought I'll do is I'll just take the 3 most different approaches that I can think of and compare and contrast them a little bit so that we can see where we fit in. The first and probably the most well-known one is Tesla with autopilot. And here, in a lot of ways, you can think of Tesla almost as the iPhone of self-driving. They control everything. They make the car, they make the software, they can plan, or they have full control over what sensors is in the car, what software is running, how they plan on going from point A to point B. They control absolutely everything. And in a lot of ways, that is the iPhone of self-driving. Maybe I should use the ticker. Then in the middle, we have a company called Comma AI. Now, if Tesla is the Apple of self-driving, then in a lot of ways, Comma is sort of the Android of self-driving. They try and work on everything. They have a bunch of the distinguishing features. First is they use a software called OpenPilot, completely free, open source, available on GitHub. You can go and download it, you can open it up, and you can have a look at it. I made my GTA car use their model to actually plan at one point. So it is completely free, it's available, and you can go and have a look at it. Secondly, they try and work on almost any car. They have this little harness that you can plug into the CAN bus of a car, and it takes the signals from the car and it sort of hijacks them a little bit. They work on most of the models that are released in the last 5 years. They've got support for over 50 different cars, so they work on almost anything. And the idea here is actually incredible, because what they cannot do is they cannot guarantee what sensors is in the car. So they have the opposite approach to Tesla, which can control everything. They have to rely on something else. And in their case, the something else is vision. They have a little device that you can buy that you sort of fit onto where your mirror should be. This has cameras that point to the road, and it uses vision to plan its routes from A to B. It still uses sensors, but it uses vision as its primary source for how it's getting from point A to point B. Now, this has interesting implications. I mean, now they are trying to teach a car how to drive the way that a human would drive. You stay in lane lines not just because they're yellow lane lines, but because most people stay in lane lines. They stop at stop streets, not just because it's red or it says stop at the bottom, but because a lot of people actually stop at the stop streets. The way they do it is people can record their videos, send it up to them, and they train their model, and their model hopefully gets better and learns what humans are doing. And that is sort of the overarching theme that we are going to try and hit today. We are also going to use vision to a very basic principle, but we're going to use vision, and we're going to hopefully teach a model to drive like we, or play game at least, like we would play games. Hey, it works. The last company that we just have to quickly discuss is Waymo. And they are, again, on the other end of the spectrum, ironically, originally owned by Google. But what they do that is interesting is they, first of all, level 5. They are completely autonomous. And they try and play in the space almost like an Uber would. You simply have an app on your phone. You can call the car, and it takes you from point A to point B. Now, they have a reliance on the environment in which they work. They don't work everywhere. You think of it, the car is not owned by anybody, so it's sort of in a warehouse or it just drives around. So you need somewhere for those cars to go. But over and above that, it knows the area in which it works very well, so it has a reliance on the environment. Secondly, it's not going to win the prettiest car in the world. It's this car on the left-hand side. It's got like a big hood on top that has LIDAR sensors in it, so it has a different type of sensor. It has over 20 cameras. But still the idea is partial vision here and partial knowing the environment and then a combination of the sensors to actually figure out where you're going. The interesting thing about self-driving is that a lot of people are trying this out, and there's a lot of places where you can get information about it. There's interesting people you can follow. I mean, obviously Elon Musk is a figurehead for Tesla, but there's Lex Friedman, MIT professor. There's George Hotz, that's this guy in the middle here. He, on one day, just locked himself in his garage and thought, well, this can't be that hard, and he tried to make his car drive. And a couple of hours later, he could actually get his car to drive a little bit. So he's an interesting guy to follow. He would live stream those events where he tries to learn these things. He did a Twitch slam as a localization technique. He just simply streamed it for 4 or 5 hours while he tried to build it. There's also hardware manufacturers in here, so like NVIDIA. I am going to try and drive the car from my machine, which is a Windows machine. It's a work laptop. Understandably, I couldn't convince my company to buy me a gaming laptop, so I'm offloading some of the work to a little board that is almost like a Raspberry Pi size board, made by NVIDIA. It's got 128 CUDA cores, so it's really good at training data. And it allows me to cut down my training time of my model a little bit. Next up is just driving in general. And it's the same way you learn to drive when you learn to drive. You learn to change the gears, you learn to look around in the mirrors, you learn the road signals, stuff like that. Training cars to drive themselves have similar problems. Now, just to give you a high-level overview of how complex this problem is, you can think of the problems they're trying to solve as tasks. It's generally defined as tasks. And it's the same way we would learn to drive. There is driving tasks. So that is stuff like your steering wheel control. You obviously, when you drive your car yourself, you have to be able to turn your steering wheel to the left or to the right. This is your lateral control. Self-driving cars have the same problem. You have to do movement, so you have to be able to accelerate yourself forwards and backwards. Same problem, gas, brake. Then there's a bunch of problems that are in the space of just how do you drive? How do you stay in lane lines? Now think of lane lines as an example. We think of lane lines as these yellow lines on the side, and you try and figure out how to stay in between them, and you simply try and drive. But it's not just that simple. Not all countries have lane lines. Not all countries' lane lines are yellow. What if this road works and the lane line is closed? How does your car actually interpret this? What if it's snowing, as example? We don't have a lot of snow, but there's countries that have snow. And then the road lines are completely covered. Now all of a sudden your car can't drive. That is a problem. But if you do a vision solution to this, maybe the car learns that the tracks on the snow is actually the thing that it should follow. Lane lines also get a little bit more complicated. I mean, you have to obviously follow the lane line, but what do you do if you change lane lines? What if they're not there? All sorts of problems like that. The last section of problems is in the traditional computer vision space. So this is a very academic field, but this is stuff like image classification, image recognition, collision avoidance, or object detection. You want to know if the person in front of you is a car. You can detect that from vision. Maybe there's a bicycle that's coming from your left-hand side, and you want to recognize that it's a bicycle that's going across. But think of the same problem. What if you're driving past a bicycle rack, and they are stationary bikes sitting in a bicycle rack? All of a sudden, your car starts thinking that all of these bicycles want to drive across the road. So you have to understand your scene a little bit around you. But the general field here is computer vision, trying to detect things, road segmentation or image segmentation, just figuring out where the actual road is versus what is the side vision of it. The way that a lot of companies are trying to solve this, or the way that most car manufacturers are trying to solve this, is by putting in more sensors into the car. And this makes sense. The better you understand your environment around you, the better you can control the car. These type of sensors are typically divided into groups of 4 main groups. There's more, but there's 4 main groups. And the main one we are interested in is actually the vision one at the top. Now here, who here has a car that if you put it in reverse, it either beeps for you when you go backwards, or it shows you an image of going backwards? It happens quite a lot. So cars come out with these type of sensors now built in. Reverse cameras, the first one. A lot of cars are coming out with blind spot cameras so that you can see what is behind you. Cameras facing forward, either narrow angle of the road, wide angle of the road, or even stereo vision. And then a group that a lot of people are forgetting about is the actual driver monitoring. So either the camera from your visor or from your steering wheel, having a look at you to see if you are actually paying attention to the road. This in the future can be extended to things like facial recognition. Only you can turn on your car, or it maybe moves your seat back or forwards based on if it's you. But the idea is that a lot of cameras are also facing the person that is driving the car. The second set of sensors is all about perception and localization. And what I mean by that is a lot of cars, as they move forward, they just want to understand what is around them. And the way they do it is typically with sensors that sort of sends out a signal out to the world, and it reads back what is the composition of these things around them. So sonar, radar, LIDAR, they all work on the same principle. They have different costs, they have different ranges, they have different fidelity of their images, but in general, the idea is just you send out a signal and you try and understand what is around you. This picture at the bottom here is actually how a LIDAR camera's picture could potentially look. LIDAR, although the most expensive one, can even tell you what the composition of the thing in front of you is. So you can tell you, is it metal, is it plastic, whatever the case may be. The next group of sensors that we have to look at is motion. Now here, think of your phone. Your phone knows if it's landscape or portrait, and it adjusts your UI based on those characteristics. The car has the same problem. It wants to know if you're going uphill or downhill. Because if you think of something like adaptive cruise control, you first of all want to know that the car in front of you is 50 meters away from you, but you want to stay 50 meters. So what if you're going uphill or downhill? You can't just give it the same amount of gas. So you need to know how your car is orientated. And a lot of cars do this using accelerometers or gyroscopes, exactly the same as your phone. Cars can also extend this into what is called IMUs, or inertia motion units. These are sensors that know how to fuse together your gyroscope and your accelerometer, and it gives you back one answer. Something like, what is my orientation, or what is my roll, pitch, and yaw of my car? It can actually answer those questions for you really, really easily. The last group of sensors that we just have to quickly touch on is the actual car. Now here, it sounds obvious, but you can obviously talk to your car, and you can ask it questions. You can ask it, how's my engine doing? How hot is the temperature? How much gas do I have? What's the oil level? You can ask it these type of questions. Also very important is you can ask it how fast it's going, because you might want to know that. And then also, a lot of cars come out with GPS. You can take the GPS signal, link it to a map, figure out that you have to drive 50 kilometers per hour on this piece of road. So there's a lot of these sensors, and their purpose is to help you do the tasks at the top. Okay, so the second section of the talk that we just have to look at is GTA. And here, more or less like this self-driving, GTA wasn't really the focus. All I needed was a road, some sort of a vehicle that I'm traveling in, and some way of accelerating or deaccelerating. So it could have been a bicycle game. I don't know what the equivalent of a bicycle game is, but some sort of a bicycle game. I really didn't care. I just needed some sort of a road, some sort of a vehicle. It could have been Fortnite or Mario Kart or any one of these games. There's very interesting realistic driving games where it's more of a competition style driving like GT or Forza. GT by Sony had a self-driving car or self-driving agent just recently called GT Sophie that they trained using a reward system, and it actually beat the world champion in GT eventually. So there's a lot of options available here for us. We ended up choosing GTA, which is sort of in the middle. It's a game I chose for a bunch of reasons, but probably the most important one is it's quite open world or moddable, which means I can create, or there's mods available from a very big community to do all sorts of things. The one that I was interested in was the hood cam, so it gives you the gameplay from the perspective of the car, but there's also mods or trainers available that can do stuff like change the weather, spawn me at a specific time, so I can drive in the morning, at night, I can drive when it's raining or when it's whatever the case, whatever the scenario can be. So I can create quite a lot of training data simply using these trainers. There's also mods that give you texture packs so that you can make it more realistic, so there's a lot of advantages of using this. So it ends up being really realistic in a lot of ways. Its map is also open world. You can drive from the one end of the map all the way to the other end in roughly about half an hour, which means in a very short period of time, I can create a wide variety of training data for my model to try and learn to drive. One thing to keep in mind, if you do decide to do self-driving as a business, there is real consequences to having real cars drive on the road. You can actually hit people, and this is very detrimental to your reputation. In GTA, I can still hit people, and I'm guaranteeing you I'm still going to hit people, but at least it is not real, in air quotes anyway. And then probably the most important bit, or the overarching theme of this, is that GTA is quite a lot of fun. This is just a fun way of learning something new. And it's hopefully the overarching message, at least for this talk. Now, my plan for this was really simple. I wanted to get the gameplay while I was playing, and I wanted to feed that to a model. And then, so here for the gameplay, it could have been anything. I could have used Game Center to just record clips. I could have pointed a camera at the game while I was playing. It really doesn't matter. The idea was just I needed to get the video from it somehow. So let me quickly show you how to get that done. Okay. I'll switch to Visual Code, and I have what is called a zero-in-queue screen publisher. Now, I used, maybe this is implementation detail that I just have to go through. Processing these images takes a little bit of time, so I just want to decouple the process of getting the image versus processing the image. So I'm not processing the live video stream at this stage, I'm just simply grabbing the image and throwing it on a queue, and then the other end, I'm just receiving it. This just decouples it nicely so that I can process it very, very easily. And I ended up using a Python script with a Python binding called pywin32, where you simply give it the window name that you want to grab, what resolution it is, and it gives you back the image as a sort of an array of numbers. Really, really simple. And then, so here's the script that I'm using. grab screen. It's from Pi-Win32, but it could have been a Node.js application. It doesn't really matter. It could have been anything. Once I have the screen, I allow it to do sort of like a command line tool, so you can give it stuff like, should it show you the video while it was sending it, what the address is, what it needs to send it to, what the width and the height should be, just some details about it. Then very important, what the game is. The fact that this is decoupled means the game really doesn't matter. If I was spinning up GT or Forza, I could just simply point to the window and I can record the game. Once I have those configurations, I set up a 0MQ publisher. So this is just a pub sub pattern. It's a slight complication on the implementation, but it is very consistent. So hopefully that doesn't make a difference. It has a little helper to just send the image. It has a loop that runs. And while it's running, it simply grabs the screen at the resolution that I'm asking it for. And it's using OpenCV to just resize the image to the size that I want. Very, very simple. Let's run this. So notice here I've got GTA running. This is part of the complexity of my demo, by the way. So GTA only works if you're actually opening up the window, and I need to do two things on one machine, so keep that in mind. I can't move my mouse out here. I have to Alt-Tab. But we'll move it to the side. And we'll switch to a command line. And in our pub sub directory, the script we just saw, it's Python 0MQ screen publisher. And it goes off and it gets the screen and it just pushes it out to the publisher. Now that it's on the publisher, I can get it from my Jetson Nano little PC or from any PC that I want. But it simply sends out the screen. On the flip side, we have exactly the same pattern. There's a 0MQ screen subscriber that does exactly the same. So I'm running out of screen real estate here a little bit. But it has a little helper that knows how to decode the image that I'm sending it. It has the command line arguments exactly like the previous one. It opens up a subscriber. The only implementation detail here maybe that is important is it conflates the messages, which means it only takes the last one, but it's just implementation. And then it runs in a loop to receive the image. If we run this, screen subscriber, screen publisher, and to just drive the point home next to each other, different windows. And if I open up my game, it is slower, I get that, but I wasn't really interested in absolutely real time here. I was only trying to record at roughly about 7 frames per second. There's somebody just bumped me, but it doesn't matter. And the idea is very simple. I'm now able to get to the video stream. Part 1. We are definitely going to run out of time. Maybe while I'm running out of time, I should just point out that I'm going to release the whole slide deck, plus the training images, plus everything that I've used. And you'll notice, although they're hidden, there's a screencast for every single one of these steps, so you can, at your time, if we run out of time, just go through them if you want to. Okay, so next up, we have a way of getting the video. Now, the video on its own is not helping us really, because the machine will never be able to, or not never, but it will struggle to figure out what we are trying to do. So my idea was take a frame and tell it what I was doing to the game. Just record the directional keys on the keyboard. And that way, whatever the game is, I can teach it to do that game. Now, this worked. It gave me a model that understood these keyboard keys, the A, W, S, and D, which controls the motion of the car, but to play back the game started becoming a little bit complicated, because I wasn't recording exactly how long I'm pressing the A or the W or S. So the car moved, it tried to avoid cars in front of it, but it was very jerky, the motion, because you never know exactly how long you should press the button. Think of acceleration as an example. If I press the W, all it does is press the gas on the game. So this thing would rev up all the way to the top, and it would start driving 100 kilometers or 100 miles per hour, and that was simply too fast to figure out if my model was actually working to control the game. Then I switched from the keyboard, these 4 keys that I'm sending in, to a game controller. This gave me the same 4 values basically, but at least it gave me as a scale from 0 to 1, which means I can press the throttle at 40% or 50%, I can press the brake at 40 or 50%, I can turn left or I can turn right at a certain percentage. This gave me better control. I could drive my car at maybe 50% acceleration, which made it drive a little bit slower, but I still had the essential problem of I can only turn left or I can only turn right. Okay. So to solve that, I had to go and rethink a little bit about how I am training my model. And I decided that control was simply not enough. The stuff that I needed, well, first of all, was speed. I didn't want to drive 50 miles per hour or 100 miles per hour. I wanted to control the speed that the car was going at, which means I need some way of getting the speed from the game. Now, this in concept sounds very, very easy. All you do is you look at the speedometer at the bottom of the screen, use OCR, figure out what the number should be, and then you can interpret that as speed. That does work, but it is a little bit slow. So I decided that since GTA is moddable, I'm going to write a mod to try and do this. And this gave me the speed, which works really, really well. But as a side benefit of it, it also gives me a bunch of other information, which means I could now make real decisions about how I train my model. And I decided the stuff that I'm going to train it on is the steering angle, the exact angle to 90 degrees to the right or 90 degrees to the left, which the mod actually gives me back. Normalized to 1 or -1, but still. And then the amount of throttle and brake that I'm actually pressing at that specific time. This gave me back an image that looks almost like this one on the right-hand side, which meant I can tell my model can predict that I should turn 20% to the right, and the little blocks, although my math absolutely sucks, it's supposed to be sideways lines, but the color of the blocks actually shows you if it's accelerating or braking, which means I started getting back a lot of information about the car that was really useful. The way that I did the script, or oh, we're running out of time. Okay, but anyway, the way that I did the script was a simple script-to-V script. This is a wrapper for GTA that allows you to write .NET code, which is nice, and you can hook into the game, and you can get all sorts of stuff like your speed, your steering angle, your brake, and your throttle power, but it also gives me other information, like, for instance, my engine health, my gas level, my fuel level, my temperature of the car, my location where I am. It gave me a lot of other information that I was not interested in, but it could give it back to me. Let's quickly look at this. We should still be okay at time. The script that I'm using, script-to-V, very, very simple, .NET library that wraps everything for you. And if we switch to Visual Studio Code, somebody told me I had to use the light theme. I don't like the light theme, but it's still, I'm using it nonetheless. To get script-to-V is just a NuGet package that you add. So there it is. Once I got the script working, I could figure out how I want to send the state back of the car. This is just an object that I'm serializing to JSON. So I'm simply sending JSON back exactly the same way we did with the video. It has a timestamp for me to just check where I am, and then the values that I'm interested in, stuff like steering angle, brake power, throttle power, etc. It also has interesting ability to tell you if you're in a vehicle or not. This is not necessarily translatable to real world, but it was useful because then I could only drive when I'm actually in the car. And then I had some simple feature toggles that I just bind to the F10, 11, and 12 keys. The idea here was to do something like turn cruise control on or off, or turn autopilot on and off, etc. And to do the script, it's just a .NET class library deriving from GTA script, GTA.script. It has an event handler that fires on every time the game loop runs. And it has a binding for the key hook, for the keyboard down and up. Exactly like a subscriber and publisher, from the screens, it has a little helper to publish the messages across 0MQ. And it has a little helper that updates the state. And the logic here is very, very simple. It just checks, do I have a character? Is the character in the vehicle? What vehicle is it? And what is the current power, brake, steering, etc. As far as the key hooks are concerned, F10, 11, and 12 just binds to each one of the keys, and it just flips that little toggle for us in our script. Now, once you have your script, it's just a DLL that you copy into GTA. So my GTA running here is already running the script. If we switch to another Python video or directory, sorry, my PC is now getting a little bit strained here. I run the 0MQ subscriber. It does not automatically, since I'm not doing anything in the game, it's not showing anything. If I switch over to the game and I start driving around, you should see my steering angle, my brake and my throttle come back. And these are just the values that I'm using to train the model. We'll get to that in a sec. To drive the point home of how nice the subscription is, the exact same demo in a second, but as a Windows app, since it's just subscribing to stuff, it now can do the exact same thing in Windows. Okay. I'll try and speed up a little bit now. Okay. Okay, so now we've got the screen, we've got the state of the car, and we can start recording these things so that we can use it for our machine learning a little bit later. And the idea was simple. For every frame that I have, I take the car state and I save it as what I call the trip, but it's just me going from point A to point B. And like I said, this will be available afterwards, but there's a bunch of trips available. I did it at night, I did it at the morning, I did it in the afternoon, I did it as Trevor, Michael, and Franklin, the 3 characters in GTA, and I also did it with their own cars and stolen cars just to vary it off a little bit so that I can see what is different about the cars. And the idea is exactly the same. For every one of those trips that just has an ID, it has the video frame and the accompanying car state for it. These trips ended up being anything between 10 and 12 minutes. It is deceivingly harder than you think to stay in GTA, stay on the road, stop at stop streets, and stop at the traffic lights. It is quite hard. So they ended up being a little bit shorter, but it's roughly about 10 minutes to 12 minutes of driving. And then I take those 12 minutes and I just divide it into 1-minute segments. And the reason why is just so that I can analyze it a little bit better. Because remember, I did not know up front what I didn't know. So I wanted to experiment with what type of training data I've got. As far as the data is concerned, one of the things that I only learned afterwards is that you want to have very balanced data. You don't want to just train your model on going straight, because that is what it will eventually do. It will just try and drive straight. So you want a nice balanced data. And for that, I unfortunately needed to look a little bit at my training data. For that, we'll switch to the Jupyter Notebook. So this Jupyter Notebook is running on this little Raspberry Pi style PC key with the GPU. And there's a project that is then downloadable, GTA Bot, and it's got a bunch of trips inside. These trips are just those 1-minute segments of driving that I've got. And each one of them have a corresponding CSV file or an Excel spreadsheet that sits with them that just tells you this frame, I was going this speed, I was turning this direction so that I can train my model. If we do exactly the same thing in the notebooks, by the way, for those of you who don't know, Jupyter Notebooks is a Python runtime, if you will, that has a very nice concept of giving you examples of what you want to do. You can describe it in natural language, and then it has an interpreter that runs just a piece of Python code that you can do, which means this code that I've got here is encapsulated completely in a notebook, and that is encapsulated in a Docker container, which means anybody here can just get it and run it exactly like I'm running it now. You load the trip notebooks basic notebook. I have a little helper that just gives me a list of all the trips, and I can choose any one of these trips. In my case, I chose the A84 one. Doesn't really matter which one. And you simply run that piece of code. This just loads the libraries that I need. Next up, we use pandas to load the CSV file. It's a very nice statistical analysis tool that you can use in Python. If you're interested in the statistical side of it, Mike after me here in this room is actually showing a lot of nice statistical stuff. But for this pandas, we can now use the describe method to look at our trip. And we will see stuff like we were driving 50% at 5 kilometers per hour, we were going max 26 miles per hour. We can get more statistics about it, like the full trip length. And then what is important for us is actually the steering distribution. We want to know were we driving right, straight or left or right. For the sake of time, I'm going to skip a bunch of these ones. I just want to show you 2 specific ones. For each trip, you can get a specific frame and show it using OpenCV. So there's examples of how to do this. This looks like Michael's car, but I'm not sure. You can then also get for that specific image what the car state was, so you can correlate these together. And then lastly, you can get to each one of the segments. And if you look here, this is the 1-minute segments. So we can take one of them and simply look at how I was driving at that specific point. I am sort of in the road. I'm trying to go a little bit to the right. And you can take this and give it to the model and hopefully train it a little bit. Oh, only 5 minutes left. Oops, wrong button. Like I said, everything will be available afterwards, but I do want to get to 2 things just. The last section is the deep learning bit. Now here, I'm no expert in deep learning, but in general, at least for our concept today, we can think of AI as the big overarching academic field. Machine learning is something that it evolved over in time into. This is a lot of trying to figure out the context of messages, stuff like spam filters. And then the one we are interested in is deep learning, the one at the end. And what happened in the last 10 years is there's a bunch of models that understand how to extract features from images. And the way they do it is they look at stuff like edges of your, take my face as an example. It finds the edges of my face, my eyebrow, my eyes, my nose, my mouth. Then there's deeper layers inside this model that takes these features and makes some sort of understanding of it. It says, if there's an eyebrow, an eye, and a nose close together, it's probably a face. And this is sort of the context or the idea that we're going to explore today. A lot of these examples is it a cat? Is it a dog? What breed of dog is it? What breed of cat is it? We're going to use the same idea. We're going to give the model, the pre-trained model, we're going to give it the GTA image. We're going to hope that it's going to see something like the traffic light in the picture. And if the image is red, it would see that a lot of people brake at that point. If it's green, it would hopefully see that people are going at that point. And that way, using regression, it's going to hopefully learn a little bit more about how we want to do this. The specific field we are going to try and use is what is called transfer learning, which means we use models that are already understanding how to extract the features. We don't have to train it, what is a car, what is a traffic light, what is a road. We are going to use models that already understand that. The only thing we're going to do is, instead of asking it to predict, is it a cat, is it a dog, is it a table, is it a chair, we're going to ask it, predict to me what my steering would be, what my throttle would be, what my brake would be. Okay, so the trip details that we recorded earlier, we take the screen, we take the state, we give it to it, and we ask it via regression to try and figure out how the next frame would be interpreted. These models that we're going to use that's pre-trained, you typically look for them in stuff like the ImageNet classification competitions. They have these competitions every year where they have data sets that are really, really big, and they have competitions to see who can do it the fastest, who can do the most classifications. There's a bunch of winners, ResNet, AlexNet. We're going to use ResNet. The last bit is that you want to do the training, you want to offload it to the GPU a little bit because it takes a little bit of time. There's many frameworks to do that, PyTorch, TensorFlow. I'm using PyTorch only by virtue that I have examples in it. Okay, let's quickly look at this. Oh, okay. Maybe I should stop one or two of these things. Let's leave that one open. Apologies, my machine is taking a little bit of strain here. While we wait, any questions? Nobody brave. Okay, no problem. Okay, so let's look at the road following examples. Here's the training model. Again, same idea. PyTorch has got examples of this, or Jupyter Notebook examples, but we simply load the PyTorch libraries that we need. Once we have that, we create what is called a data set, which is just exactly like we just looked at the trips. It's the same idea. It's a thing that knows where to find the trips. And then for each one of these trips, it can tell you stuff like how many trips or how many frames there are in the data set. It can get the data set, so it can get that image, exactly what we did earlier. Okay, and it gets the steering angle, throttle, and brake for each one of those frames. It uses a little bit of tensor magic to convert it into the format that PyTorch wants it. And now we are ready to try and train our model. What you typically do when you train a model is you have a data set that is the data that you train it on, and then you have a couple of test cases that it needs to test. So all we're going to do is, since we know exactly what our steering angle for each one of those frames is, we take all our frames, we divide it 90% as training data and 10% as test data. And then you can run this over and over and over, and it can predict what the steering should be. You need data loaders for this. So there's a training data loader, and there's a test data loader. This allows me to load the images. So what it does is it can tell you stuff like, should it shuffle the images? How many threads should it use? How many of these Jetsons do I have that I want to distribute the work on? And then I load the model, and I know that it's a pre-trained model. And then here's where the magic happens. That's the only line you really have to remember. It says the 512 last neurons that it has, instead of predicting the 1,000 classes, just predicted 3 things for me: steering, throttle, and brake. And then I can start running it. You can run it as many times as you want, but this does take time. So this one is set to 1, but typically you would run it 50 or 70 times. And then it runs the train step, where it gives it an image and then the labels, which is the car state, and then it runs the evaluation step. And if your loss function is low enough, it saves the model for you. This one here, that one there. Okay, like any cooking show, I have one already here called Best Steering. This was run over 10 epochs, 20,000 images. It ran for almost a day and a half on this machine, which has got 128 core CUDA cores. I am definitely not getting to everything. I'm probably almost out of time. Hey? But that being said, if you have time, there is also a accompanying notebook that shows you how to run this. So what it does is set up the PyTorch again for us. It loads our model this time. So instead of having the model pre-trained, it gives us our model that we trained. It sets up a little transformation that just knows how to take that image and make it so that it's PyTorch friendly. And then we create our 0MQ subscribers to the camera state and the camera. And also the 0MQ bot, which is the thing that tells it how fast it should go. Should it press the throttle or brake? Then there's I'm skipping a lot, excuse it. But there's a method that runs every time this picture gets sent back now, that simply goes and says, run my model on this image. And what I get back is a car state. So now I get back a prediction what my steering angle should be, what my throttle should be, what my brake should be. And then I can go and use that to control the car. Now this isn't as simple as it sounds. You can't just tell it turn left, turn right. You have to sort of gradiently go left and right. But the general idea is I give it a picture, I ask it what it should be, and I'm executing this afterwards. I'm grinding my machine to a halt now. But I do need to just summarize if I can. So here is an architectural view of what I just did. The bottom one is my PC, the top one is the Jetson Nano, and you'll see that they just sort of mirror each other. There's a pub sub for the car state, there's a pub sub for the screen, and then there's an inverse, one that sends back the control signal to the game. And it just uses virtual joystick to control the car. But I don't think we'll get there right now. And then as far as the pattern is concerned, it's the same for anything. We collect a bunch of data, our trips, we train our model with those trips, and then we evaluate the model to see if it's good enough. And if it isn't, we just collect more image, we train it more, we ask it more questions. I'll exclude that. And then maybe the main takeaway here is that machines can learn what humans can do. So think of something like, we were in Cape Town just now, and they make a lot of wine, and they need grapes for that. You can have a machine that looks at the grape and learns what is a good grape or a bad grape, or what type of grape you need for what type of wine. And it can automatically sort these things. You can automate these processes where you visually have to look at something, you can learn about it, and you can automate it. Think of security systems. I might have a camera pointing to my driveway, and my dog walks across. That is okay. But if somebody pretends to be a dog and leopard crawls across the pathway, that is not good. And this type of machines can hopefully figure that out. And I think that is it. I am running seriously out of time, but if there's questions, you're welcome to ask now or grab me afterwards. I will be around here. But I do think I am out of time. Nobody's showing me if I'm out of time or not, so it's okay. Now somebody's looking up. Okay. Any questions? I don't know where the mic guy is. Nobody's stopping me either, which is very cool. I don't know if I can. Now, I skipped all the steps to read the codes, and now I have to go back and run the interpreter for each one, but you're welcome to have a look afterwards. I'd rather not risk running it right now. You're showing me this, which probably means stop. Sorry about that.